In this video, we introduce modular arithmetic. We let a and b be integers and n be a positive integer. We say that a is congruent to b modulo n, written as a 3 horizontal lines b, then bracket mod n, if n divides a minus b. In other words, a minus b equals k times n for some integer k, which is equivalent to a equals b plus k times n. It also means that a and b leave the same remainder when divided by n. For example, 7 is congruent to 1 mod 3, since 7 minus 1 equals 2 times 3. 20 is congruent to 0 mod 4, since 20 minus 0 equals 5 times 4. Also, 15 is congruent to negative 12 mod 9, since 15 minus negative 12 equals 3 times 9. There are some properties which are immediate from the definition. First, a is congruent to a mod n for any integer a. Second, a is congruent to b mod n if and only if b is congruent to a mod n. Third, a is congruent to b mod n and b is congruent to c mod n implies that a is congruent to c mod n. Lastly, for all integers a, there exists a unique b where b is greater than or equal to 0 and less than n, such that a is congruent to b mod n. In this case, b is just a remainder when a is divided by n. We first give a few useful results in congruence regarding operations. If a is congruent to b mod n and c is congruent to d mod n, then a plus c is congruent to b plus d mod n, and also a times c is congruent to b times d mod n. In particular, a to the k is congruent to b to the k mod n for all positive integers k. To prove this, we first use the definition to write a equals b plus k times n and c equals d plus l times n for some integers k and l. For the first statement, we write a plus c equals b plus k times n plus d plus l times n, which equals b plus d plus bracket k plus l times n. This implies that a plus c is congruent to b plus d mod n. For the second statement, we compute a times c, which is equal to bracket b plus k times n times bracket d plus l times n, which is equal to b times d plus 3 other terms, all of which have a common factor of n, so we can take out n to get bracket b times l plus k times d plus k times l times n times n. This implies that a times c is congruent to b times d mod n. We have seen that we can do addition and multiplication in congruences just like for equalities. Division, however, is less straightforward and is addressed in the following proposition. It states that if a times c is congruent to b times c mod n, and the HCF of c and n equals 1, then a is congruent to b mod n. In other words, we can only cancel a common factor in congruences when the HCF of that factor is congruent to the modulo. The proof of this result is surprisingly easy. If a times c is congruent to b times c mod n, then it implies that n divides a times c minus b times c. In other words, n divides c times bracket a minus b. Since the HCF of c and n equals 1, from a result in the second video, we know that n divides a minus b. This implies that a is congruent to b mod n. Let's consider some examples. we try to find the remainder when 15 to the power 99 is divided by 7, and 2 to the power 100 is divided by 15. For the first one, we know that 15 is congruent to 1 mod 7, so we can raise both sides to the power 99 to get 15 to the 99 is congruent to 1 to the 99 mod 7, which is just 1 mod 7. In other words, the remainder is 1. Secondly, the first power of 2, which is greater than 15, is 16, which is 2 to the 4, and is congruent to 1 mod 15. Hence, we can write 2 to the 100 as 2 to the 4 to the 25, which is congruent to 1 to the 25, which is just 1. In other words, the remainder is again 1. As another example, let's find an integer x such that x is greater than or equal to 0 and less than 11, and 5 to the 23 is congruent to x mod 11. We can do so by the method of successive squaring. We first write 23 as a sum of powers of 2, so we write 23 equals 16 plus 4 plus 2 plus 1. This implies that 5 to the 23 equals 5 to the 16 plus 4 plus 2 plus 1, which equals 5 to the 16 times 5 to the 4 times 5 squared times 5. Now, we can find these powers of 5 by squaring. Firstly, 5 squared is 25, which is congruent to 3 mod 11. Then, 5 to the 4, which is 5 squared, is congruent to 3 squared, which is 9. Since we will keep squaring numbers, it is useful for us to write this as -2, which has a smaller size. Now, 5 to the 8, which is 5 to the 4 squared, is congruent to -2 squared, which is 4. Lastly, 5 to the 16 is 5 to the 8 squared, which is congruent to 4 squared, which is 16, which is congruent to 5 mod 11. Hence, 5 to the 23, which is 5 to the 16 times 5 to the 4 times 5 squared times 5, is congruent to 5 times -2 times 3 times 5. This product is -150, which is congruent to 4 mod 11. In other words, x is 4. Now, let's look at a proposition involving the equation a times x is congruent to 1 mod m, where m is a positive integer and a is an integer. This equation has solutions if and only if the HCF of a and m equals 1. Let's first consider the only if direction. A times x is congruent to 1 mod m implies that ax plus km equals 1 for some integer k. Note that the HCF of a and m divides a times x plus k times m. This implies that the HCF of a and m divides 1. So the HCF must be 1. Conversely, suppose that the HCF of a and m equals 1. Then, using the extended Euclidean algorithm, there exist integers x and y, such that ax plus ym equals 1. This implies that ax is congruent to 1 mod m. Now let's consider the following question. Is 5 times n plus 3 a square for some positive integer n? Suppose that is the case. In other words, there exists a positive integer k such that 5 times n plus 3 equals k squared. This is equivalent to k squared is congruent to 3 mod 5. There are 5 cases to consider, namely when k is congruent to 0, 1, 2, 3, or 4 mod 5. If k is congruent to 0 mod 5, then k squared is congruent to 0, which is not congruent to 3 mod 5. Second, if k is congruent to 1 mod 5, then k squared is congruent to 1, which is again not congruent to 3 mod 5. Third, if k is congruent to 2 mod 5, then k squared is congruent to 2 squared, which is 4, and is not congruent to 3 mod 5. If k is congruent to 3 mod 5, then k squared is congruent to 3 squared, which is 9, which is congruent to 4, and not congruent to 3 mod 5. Lastly, if k is congruent to 4 mod 5, then k squared is congruent to 4 squared, which is 16, and is congruent to 1, but not 3 mod 5. Hence, in all 5 cases, k squared is not congruent to 3 mod 5, which means that 5 times n plus 3 is not a square for all positive integers n. As the last example, let's show that the equation x squared plus 5y squared equals 3z squared, which we label as star, has no solutions for integers x, y, and z, except when all of them are equal to 0. To show this, let x, y, and z be non-zero integers and is a solution to the equation. In this case, k times x, k times y, and k times z is also a solution for all integers k. So we may assume that the HCF of x, y, and z equals 1. Note that the equation star is equivalent to x squared is congruent to 3z squared mod 5. Suppose for a contradiction that z is not congruent to 0 mod 5. Then z is not a multiple of 5, so the HCF of z and 5 equals 1. Then, using the previous proposition, there exists an integer y such that z times y is congruent to 1 mod 5. Now, the square of x times y, which is x squared times y squared, is congruent to 3 times z squared times y squared, which is congruent to 3 times 1 squared, which is just 3 mod 5. This is a contradiction because we have seen that 3 is not congruent to a square mod 5. This contradiction means that z must be congruent to 0 mod 5. Thus, x squared, which is congruent to 3 times 0 squared, is congruent to 0 mod 5. This implies that x is congruent to 0 mod 5, which is clear from the previous example. Now, we can write x equals 5 times x naught and z equals 5 times z naught for some integers x naught and z naught. Now, we can substitute these expressions into star to get 5 times x naught whole squared plus 5 times y squared equals 3 times bracket 5 times z naught squared. Then y squared is equal to 15 times z naught squared minus 5 times x naught squared, which is congruent to 0 mod 5. Again, this implies that y is congruent to 0 mod 5. We have shown that 5 is a common factor of x, y, and z, which is a contradiction since we have assumed that the HCF of x, y, and z equals 1. So indeed, there are no non-zero solutions to the equation.